Okay. I guess we are.
I started this way.
Huh?
It has started.
It has already started.
Yeah.
Oh. Okay, so welcome everybody to today's lecture. So yesterday we saw a whole bunch of topics and definitions. Neighborhood complexity, profile complexity, DC dimension and so on, and which are all a little bit more related, they have the same flavor. So that's why I wanted to show you all of them. Okay, what's the topic of today? I will continue. So, oh yeah, and then in the end I stated this theorem, which essentially is another characterization of graph classes of harmonic expansion, which is, I think, very beautiful. So, remember we had the definition of harmonic expansion was using these shallow minors, then we had an equivalent characterization using the coloring numbers. And now there is another one using these neighborhood complexity and profile complexity. So what we saw is that so if you had bounded profile complexity for any d, you definitely had bounded neighborhood complexity for any d. And what the theorem of Reidel, Sanchez, Villamil, and Stavropoulos says is that actually having bounded linear, sorry, I said bounded, but what I meant is linear complexity is characterization of graph classes of bounded expansion. So, yeah. So 3 implies 2 is trivial from definitions. And what I want to do now to start, I want to show you the proof that 1 implies 3. That means if your graph class has bounded expansion, then you have a bounded neighborhood. That is kind of the useful side, because then you can just start with a class of bounded expansion and then you can work and assume that it has a linear, say bounded, but I mean linear neighborhood complexity, linear is the size of the set K that you're in. So I kept the definitions of, so actually we are only working today with profile complexity, so neighborhood complexity is not needed now, because I'm going to show that if you have a bounded expansion, you have bounded profile complexity, which in turn implies bounded neighborhood complexity, but that is not needed today. When I'm done with this proof, we will have Shivesh as our guest lecturer, who will present us some application of this and other things. So we will give a small presentation on his own work, where he has worked actually on bounded expansion, and he has obtained kernelization algorithms for some problems. Explain us about that. And then the third part of the lecture, I will give you another application, but this time it will no longer be on neighborhood complexity. It will be using the coloring numbers. And this will be some approximation algorithms for some domination problems, which is, I think, also nice. So I'll try to show you that. But let's start with this proof. So I'm taking a graph class of bounded expansion, D, and I will show that it has a bounded profile complexity. To do this, I will use the weak coloring number. So, let's see a graph class of bounded expansion. C of bounded expansion, and as we know, this implies that by the theorem of Zhu that we saw yesterday, I think. That means that the weak color number for every d is bounded. So, well, okay, what I will fix d. Okay, let d be a natural number. I mean, to show what I want to show, I need to show that for every d and for every set of size k, the profile complexity at distance d, the d profile complexity of this set, is linear size of the set. So to do this, I will just fix some set, and so I will take a D and I will prove it for that D. And let's take X, a set of size K. Of course, it will work for any D and any X. So I will show that the profile complexity is bound. Okay, so we know that the weak colored number of my graph, I didn't say I take a graph, of course, that X is set of size K in some graph of my class. So the weak colored number, in fact, I will not take D, I will take 2D. The weak colored number at distance 2D of G is some function of D, let's call this capital D. It's just some number, which comes from this theorem of this. This is by characterization by something like that. Okay. And so I will take some sigma, some order. That is optimal for this weak coloring thing. I think I have all my assumptions now. So in fact, what we will prove, that profile complexity at distance D of X of G with respect to X is at most the following function 1 plus capital D 2 to the power D minus 1 times D plus 2, something like that. Some exponential number in capital D. Capital D might be itself exponential in little d, but it only depends on D. So that function will look something like that. So what do we take? What is our picture? Our picture is that we have our set X, and we want to look at the profiles of X. The profiles, sorry, of vertices. So just to recall what it means, to be clear about the definitions. You have all your vertices x1 to xk in X, and for a given vertex you're looking at the, let's say, ordered vector of distances. If you want to be formal, you write it as a function. But since I've ordered my set X from x1 to xk, I can just say this is a vector with a distance. If I have u here, distance from u to x1, distance from u to x2, let's say 2, 3, 2, etc. Maybe this is too far, so it gets infinity everywhere. So let's say d is at most 3, for example. Is 3. So you're looking at these vectors of distances. How many of them can you do? Maybe some vertices actually have exactly the same. This is, for example, infinity and 1, 1, 1 in the end. So these two vertices have the same vector, so we will count at once. We want to count how many different vectors there are. And if the distance is strictly more than d, I put infinity. So that's the profile complexity. The D profile complexity with respect to my set X. Okay, but we want to use this sigma, this weak coloring order. So to do so, what I will do, I will take my X and I will enlarge it. I will enrich it by taking all the people who are weakly reachable from there. So So of course, every vertex in X is reachable, weakly reachable from itself. So I will get a set which is a bit larger, which I'll call y. This y. Let's put that here. Y is the union from 1 to k of the weakly reachability sets at distance 2d of my xi's. Well, with respect to the g sigma. So remember what is weak reachability? What it meant was that, so I have my sigma over v1 to vn. Somewhere I have my xi here, which is an x. I don't know anything about this ordering, but yes, what I know is that it's a good ordering for the weak ordering number. It is not too big. That means all these reachability sets are small. They are at most capital D. Remember what is weak reachability is that you look at all the vertices here where you don't allow anything before to be used, and here you can use anything. You take all the vertices for which there is a path from xi to that vertex, and that path should be of length at most 2d, because I'm taking weak ordering 2d. And now I know that if you look at all the possible vertices like that, there is at most capital D. Some function of d, which I call capital D, it's just a number. This guy. This. Of course, all these intermediate vertices are also in my weak reachability. So this number is at most. Size is at most capital D. This was my assumption. Okay, so this is what's happening. So now I'm doing this for all the xi's. Right? So I'm doing it for x1, x2, x3, etc.
What was the capital D thing? Because that was the function, no? If of 2D.
Yeah, I called it D.
Yeah.
Just to simplify because I don't want to write. Huh?
How do you get W reach Vi is less than D?
Oh, this is the definition. So the weak coloring number at distance 2D, by definition, here is at most some constant, which I call capital D. What does it mean by definition? It is the maximum size of my weak reachability set. So I know all of these weak reachability sets are small, at most capital D. So in particular, the one for xi is also. Oh, but wait, it contains xi. So here is this. Whatever you can reach with a path of length d, which uses only things which are after this point. I cannot use something to that. In other words, this should always be the minimum of that path. I mean, this is the usual trick that we have seen yesterday, and we will see again and again. You take this path and you always consider the minimum. I mean, this is always this trick. It's a nice trick. That's what makes it work. Okay. So by the way, what does it mean? That means that this, right? The size of this y. What is it? Well, it's at most k times d, right? Because each weak reachability is capital D. I'm taking the union of k of them by just a very trivial counting without even caring about repetitions. I get that this y is not so big. K times d. So what will be? Let me tell you what is the general strategy before I go into the details. Our general strategy would be to construct something which is called a guarding set. What will be a guarding set? So what I will take a collection here. Let's make a different color. I will take a collection of subsets of my y. Here, which might be large, whatever. I'll try to make it not that big, in the sense that there are not so many of them. So I know that the union of the sets, since this will be included in y, is not so big. But I want, so the size of these sets is not so big, but I also want their number to be not so big. So the whole challenge will be to bound this number. What will be the sets? So these will be called guards. Okay, guards. And here I'm using the terminology of Joret and Rambaud. I don't know, maybe it was also used in this proof, these guarding sets. I don't know, but they use the terminology guarding sets. That's where I got it from. So these these are guards. What does it mean? That means that you take any vertex in your graph, which is a distance at most d from x. If it is more than d, we don't care. It is infinity profile. It is a so there will be one of these yellow sets such that all the paths to x will go through this yellow bubble. So for each vertex of your graph, there will be one of these yellow things which it has to go through. I mean, there could be another path going like this, but this path will be too long. I'm only caring about paths of length at most d. If your path is too long, I don't care. But all the paths of length at most d, they have to go to one single of these guys.
D or 2D?
Sorry?
D or 2D?
D. So I'm looking at D. The 2D is just for the sake of the proof. I will use the 2D. This is for the weak color number. I'm relaxing for the D color number. You will see why. But I'm looking at D, distance D. So I'm looking at the profile complexity. Yeah, we want to prove this distance D. Sorry? So the yellow sets. So I haven't defined it formally, but they will be designed in such a way that every vertex you take in your graph, let's say which is not here, this is okay, this is small. Every vertex in your graph, you can assign it one of these bubbles. All the path to reach x will go through that bubble. All the path of length at most. If it has a long path, anyway, we don't care. Why this will be helpful? The idea will be that, well, since this is small, this will be small, and there will not be a large number of them. So that means all the distances from this, since they have to go through here, it will be the distance to x will be determined by this set of distances through that of that bubble itself. So here you have a collection of vertices inside that bubble. Whatever the distances here are with x, for any two vertices which share the same bubble, okay, what will only matter is how they connect to this bubble. After that, it's only the green vertices which matter. Simply because all the paths of MD have to go through the green vertices. So this is the idea.
So all those green vertices have same distance to x, is it?
No, they have some distance to x. The 1, 2, 6, 2, 1. Some distance, but if this is small, I don't have anyway that many possible profiles for this. Okay. And then also here, that means there cannot be too many profiles for all the vertices which go here. And that's roughly the idea.
If we take the neighborhood of x, that's a single guard, right? For every vertex.
Yes. Root of x. Yes, but that might be very, that might be big, right? Because yeah, I don't know anything about that. X could have unbounded utility. So I'm going to use the weak color number. I mean, how to say? Yeah, I'm going to anyway bound the number of these yellow things. Like I know the size of each yellow thing is small because of it's not bigger than y anyway. But there could be, you know, like 2 to the power y of these yellow things.
So yellow things are the y's.
No, y is my y. The yellow things are my guards, which I haven't defined yet. I'm just giving you the overall idea.
So guards have bubbles.
Guards is a bubble. One guard is one such set. Okay. This is I'm calling a guard.
So they are subset of y?
They are subsets of y.
But not in x, is it? Or in
No, they might be next to them.
might be.
But I'm designing them in a way that for each vertex has to go through precisely one guard. Not 2, not 3. There is one guard and it has to go through this guard. That's how I'm designing it.
So these guards are
Anything. Like in the picture.
so they are disjoint.
No, you see in the picture they're not disjoint.
So then one guard, it can go through both the guards then? Through the
Well, but you can find one guard such that everything goes through this guard. Right. That's what I'm saying. So this vertex goes through this guard. Yeah, maybe it uses parts of this guard, but it doesn't matter. I can bound the
pass through the guard, it will have more than d distance.
Yeah, I'm looking only at the path of length at most d. In fact, you could, you know what you can do? You could say that. Well, you couldn't say that, but I mean, we are disregarding the path of length at least d. We don't care about them. We only look at the path distance at most.
Here, number of distinct vectors will be like at most size of
It will depend on that. I will come to the details. So let me show you how to define these cars. Okay, but see, I mean, what I meant here is that if you had two different vertices u and u prime, which they have the same guard, and also they have the same profile to that guard, then they are redundant. Because if they have exactly the same profile to the guard, that means all their path, all their distances are exactly the same to this. It means that this and this will have exactly the same distances to x. So what I will do, I will count the number of guards, and I will count the number of profiles to the guards, and that will be an upper bound on the number of profiles of profile complexity of this x. This is the idea. Is it okay, more or less? So you will define these yellow sets. You will say they are small. There are not so many. Well, especially there are not so many of them. Small we already know because they're almost the size. There are not so many of them. And for each of them, since they are small, there will not be too many profiles. So that gives me a huge bound. It could look like this, but it will be some bound which depends only on d, on that profile complexity of x. Sorry? That's yours. You'll see, but it's a usual trick. In fact, you remember yesterday in the proof we also took like 2d plus 1. If you remember the proof. It will be a bit similar. So the proof which was bounding the weak color number by this component. Sorry, vice versa. Oh, let's continue here. I'll erase that later. So what will be my guards? Okay, I will call, let's call it G for guard. So for the guard of the vertex U, what will it be? It will be, I'll take the weak reachability set at distance d of U, d not to d, intersection y. This is the guard for vertex U. So in fact, what I'm doing right now, I'm defining a huge number of guards. Right? But actually, I will show that many of them are the same. That will be fine. So because for each vertex, so this is U. Let's say U belongs to the neighborhood at distance d of x. The ones which are more far away, don't care about them. For every, and we, let's say we are counting y.
2D of x or
D. If I'm not mistaken, it will be D.
Then shouldn't we take open neighborhood will be fine?
Yeah, this is nothing. Alright. And now the important claim is that this is actually a guard. I didn't show you, right? So what means to be a guard? So, claim G of U intersects all paths of length at most d from U to S. This is what is called a guard. That's what I meant when I mentioned before. guard is the weak reachability set intersection Y.
Oh, intersections. Okay.
So the guard is inside Y. It's really like this yellow.
Okay.
Take weak reachability inside Y.
Yes.
So the guard can have intersection with X also, right?
Yeah.
So why can't we just take the guard as the set of all vertices within a distance at most d from U in X?
I don't know, but that will be too much, no?
Too less, right? X is a subset of Y.
So instead of intersection.
But X is unbounded. X has a size K. I mean, you don't want anything K to the power D or something.
Oh, X is
X is of size K.
Y is bounded, but X is not bounded.
I mean, Y is bounded, but also by a linear function of K. If you start taking like Dintz's D neighborhoods like this, you might get some exponent here, right? I want to stay linear in K.
No, he's saying like instead of, in the definition of GU, instead of intersection Y, if you take intersection X, then will it be fine?
We start on
I don't know. I didn't try. You try it. It doesn't make sense. To see if it works or why it fails. Well, I just took the proof as opposed. I didn't think too much about alternatives. Okay. So we'll take, to show you this, we take the path from U to, intersects all paths of length at most D from U to X. So that means you have a path D from U to X. So you have your U, you have some path of length at most D to some vertex X, of X, any vertex X, call it Xi. Okay, and that path. And this path is length, let's call it P. Length is at most D by my, so I want to show that my guard G of U intersects this blue path. This is any vertex of X, and this is my U. I want to show that G of U touches this blue path. Okay. But now what do you do? Well, you take the minimum of that path. So this, by the way, I drew this as this is the ordering on sigma. So that M is the minimum for all vertices in P of V, with respect to my ordering sigma. I take the smallest. This is my M. Right? But now what you observe, so since this is the minimum, this is a witnessing the weak reachability of M from U. Right? So that's the proof. Because we took as the guarding set, we took the weak reachability. Ah, no, this is not yet the proof. So, okay, this just shows that M is, so this M belongs to W reach D of U. Right? Because this is a path of length at most D, the whole blue thing, so obviously the smaller one is also of length at most D. This is minimum, so I'm fine. But now it should be in Y also, right? So my claim is that this is also in Y. But remember what was Y? Y was the union of all the weak reachabilities of the Xi's. So this is also a path of length at most D, and this is also minimum. And this is weak reachable from Xi. Xi is in X. In fact, this is much better because this is at most D, not 2D. So it's definitely in also the weak reachability of my Xi. So N is in Y, because M belongs to weak reachability to D of Xi. So that's exactly what I want. So this M, since it's in both Y and in this set, it's in my guarding set. The conclusion of this is that this implies that M belongs to G of U, and it's in the intersection. So the intersection is covered by, is hit by G of E. Okay? So that means this way of defining my guards is correct. This is what I wanted. My intention was that all the paths of length at most d from u to my x, they have to go through this. So this is a correct way to defining guard. This is what it is. Okay, so this is a correct guard. So, okay, on the observation, which I already said, but let's make it explicit. If G of U equals G of V, and the profile distances. Let's say this is some. Two vertices have the same guarding set, let's call it S, and their profile to that guard set is the same. Then the profile from U to X will be the same as the profile from V to X. Okay? Because all the paths have to go through this S. So I think it's quite intuitive that they cannot have a different distance to my x. Of course, I'm looking at most d. Okay, so how many such profiles can there be? So the profile complexity of D of such a guarding set what it is? So each guarding set is small because it is in particular included in the weak reachability. So each guard is size f of d. So let's say, this is at most capital D to make it simpler. Capital D was f of 2d, which is even bigger. So what will be the profile? Well, it will be, you have capital D choices for each vertex, and each of them is something which is like D, right? Distance 1, 2, 3, or D. Well, it could be distance 0, or it could be distance infinity. But this is at most D plus 2 to the power of this S, which is at most D plus 2 to the power of capital D. Right? This is clear? Because this is these profiles will be vectors of size the size of S, which is at most capital D. Why it's at most capital D? Because it's included in some reachability set. And for each of them, you can choose the distance 1, 2, 3 up to little d, or infinity, or 0. So that's d plus 2 possible value. And you do this capital D times, so the number of possibilities is this. that means, you see, there cannot be too many vertices which have different profiles to these guards, because these guards are small. So this is already one part of the, and you see it appearing in this part here. That's where this comes from. This will be for the, all infinity profile. This is my one. So now, this D will come from this. So what I've not... Sorry? Yeah, this KD is from this Y. So what I'm going to do, so now I have see, if I know that there are not too many possible guards, I'm finished. So this will be my goal, is to show that, you see, even though they are all, they have all been defined individually for different vertices, many of these guards will end up to be the same. If I show this, this will show that the number of yellow guards is small. Each of them doesn't create too many profiles. Each of them creates that many profiles. So I will be happy. Okay, and why? Oh, okay, because each of them has at most this size. So each guard has at most this size, and I'm doing a very rough estimate here, but upper bounding it by the size of Y. Each guard has this size. Each guard creates that many profiles. If I can now show that the number of guards is at most this number, I am finished. Well, now the rest of the proof will spend to do this. Okay, and now instead of, so the trick we will use now, there will be another trick based on the reproducibilities, but we'll take the maximum instead of the minimum this time. A little bit of change. Should I erase? Let's erase this part. Guards. Each guard is small, so this is like no size KD. Each guard creates at most that many different profiles. What is missing is the number of guards.
So each guard is of size at most D, right? Not K.
Oh yes. Each guard is at most D. Yes, because each guard was a reproducibility. Yeah, correct. Then where does my K come from? Oh, okay. No, so this K actually will come from the last. Yeah, this K comes. Thank you. The K actually comes from the last argument, which is maybe the most tricky one. Number of guards is small, and I want to show probably something like, well, whatever remains, which should be. Maybe there is a D here, so maybe this would be D squared. Okay. So let's take some guard S. S is a guard. It's a guard, so it's some G of U. So I will take the maximum. It's a max of S be the maximum in S with respect to my sigma. still the same order. So what I will show, right? So this max, it's a vertex of y since my guards are included in y. I want to show that every y in y cannot be the maximum of too many entities. Is max of S for at most 2 to the minus 1 times. So ideally, I would have liked to say that, look, so what I'm doing here, I'm taking these maxima, right? So in each of these balls, I'm taking, each of these guards, I'm taking the maximum. So if I can show, let's say I can show that each vertex of y is taken at most once, you know, well, that would show that the number of these guards is at most the size of y. That would be ideal. But I cannot do that. It could be that, you know, there are two guards which they have the same maximum. This can happen. In that case, so you have two guards, maybe they're, you know, different. But it turns out that when you order sigma, the maximum is the same. This is a guard S, this is a guard S prime. But you know the max of S equals the max of S. This can happen. But what I'm saying is it cannot happen too much. At most some constant depending on the. If it depends on it, it's probably not constant. If d is fixed, it's constant. Okay. And so if we can show this, we'll be done, because that will imply that the number of guards is at most. So this implies, by the way, that number of guards is at most this much times y, which is at most 2 to the d minus 1 times d times k. So I guess this gives a d squared, because I had already a d. Each guard was small. Oh no, each guard was small is not counted, because this is counted like, the fact that each guard is small is just used to show the bound. Right? So I just need a bound on the number of guards and the number of profiles created by each guard. So the profiles is this, here, and the number of guards is this. It's just the image. Number of guards is this. Okay. And what we will prove that how to do this? We'll prove that each S which has this guy as maximum, this guy is y, it will be included in the reachability set of y. If I can do that, this will be included in the reachability set of y. Yes, but since the reachability set of y is small, it's at most capital D, I will have just 2 to the power d subsets, possible subsets. So I'll show, so essentially what I'm doing, I take the reachability of y at 2d, instance 2d. It looks like this. Well, actually, it looks like this because y is the biggest one. This set has at most size d. I'm showing that all the guards which have chosen y as their maximum they must be completely inside the blue set. Since the blue set is small, okay, I'm being very loose here, but I'm just saying that, okay, then the number of different guards is at most 2 to the power d, because it's just the subsets of that thing. So, what I want to prove is, let's go with that. This will finish the proof.
So if you take S from,
S is a guard. It's just to have some notation. I didn't want to. I just want to call it, give him a name. What we want is S included in the reach of max S and distance to D. Yeah. Essentially, this is what it is. Or, with respect to sigma and the bracket, same order, same graph, etc. If I can prove this, then actually I will be done. So let's look at our ordering. This is my max of S. Okay. And how was this defined? You remember, max of this S is some set of U, G of U, guard of U. Okay, so it was actually looking like this. This is Y, this is G of U, Y, and this was my U, and I was taking G of U to be the subset of, it was also revirtuality from U. So that means this max of S, which is here, I don't know if we need it, this is in the revirtuality of U, so, actually bad picture, max of S will be in the middle because that means my U is somewhere here. Max of S. Okay, so you have a weak path. This. Okay. Let's go D1, let's go D. So this. Okay, so let's take any vertex little s in S. S. So this vertex S, I mean, it's also weakly reachable. So you have another path, right? This is P2. Okay. But, okay, I think now it is clear. You see that I took the maximum. Among all the vertices in S, I took the max. So if I draw my S, okay, it includes this. I don't know what it has or what it doesn't have. But this is the maximum. Like this. Now if I take any S, which is an S, it will be to the left. So now you can start with the blue path. You go wherever, you reach U, you go to the purple path, and you reach S. So what is it? It's a path of length 2D, at most 2D. It could be much shorter because maybe there is some intersection, then you do a shortcut. You take the smallest path from this guy to this guy in the purple and blue subgraph. It certainly has a length at most 2D. Okay, so if you take P1 plus P2, the length of this is at most 2D. S is the minimum of it. So S is in when you reach 2D of this Y, of the maximum. Okay. Which is exactly what I wanted to prove. I wanted to prove that capital S is completely included in weak reachability of max of S. I just took an arbitrary little s, which is in capital S, and I show that, well, it is reachable from max of S. So I do this for all the S, and it shows that capital S is really included in weak reachability of 2D of the max of S. And this completes the proof. This completes the proof by whatever I said before. Since every guard is included in this maximum, well, that means not too many possible guards have the same maximum. In fact, 2 to the power of that weak reachability size, which is 2 to the power d. Why minus 1? Where does this d minus 1 comes from? 2 to the power t is clear. Okay, but that would be a minus 1. No, that we count. The profile we count them here. So now my argument is just to say that I'm taking subset, and obviously we don't take an empty one. So that would be, but that would be 2 to the d minus 1. The minus 1 wouldn't be in the exponents. Okay, I don't know. Maybe it's something. It doesn't matter because take 2 to the d is works. Maybe the minus 1 is as you, but we don't count the empty set. And then it is here. Let's say 2 to 2. So true. Okay. I mean, the little details are not too important. Just, you know, these tricks of using the max or the min in these orders is quite nice. Oh, it's kind of clever to, you know, fiddle them around, but yeah, the main idea is that you build this guarding set, a set of cards. And if you are interested in this topic, profile complexity, you will see that in these papers, so there is this very nice paper from last year by Euler and Homburg, which they give a nice bound for the profile complexity of planar graphs. They also consider bounded treewidth, and they essentially use this idea of guarding set. So it's always like, yeah, you can choose this set of cards, and each of them gives you not too many profiles, and of course you have to use these things and play around a bit. But I think the main idea is not that complicated. It's quite good. Are there any questions about this?
So
Yes.
essentially we are trying to prove that if the class is bounded expansion, then
Yes.
the profile complexity is also bounded, right?
Yes, correct.
So that bound, that explicit bound that you obtain,
Yes.
is it required that it should be linear in case? Any function of d and k is that fine?
No. So yesterday I showed that you had so you can always show 2 to the power k, right?
Correct.
This is trivial. Okay. Yesterday I gave you an argument using the VC dimension that you have a polynomial in k to some constant. That is easy because you just show that these guys are big league free for some big league, and you get something which is k to the power, let's say, the f of 0 or something like that. Okay, but linear is much nicer, no? And remember that this is actually a characterization. So, I mean, first of all, linear is super nice, much better than, like the polynomial gets kind of trivially by DC dimension. Linear is nice, and actually, of course, the beauty of this theorem is that the reverse is also true. So if you can bound always by this linear function, by some linear function, then you're actually a polynomial.
It also helps you in getting linear kernel for many problems.
How is that useful? Like we often set a class with bounded expansion. This property.
Exactly. Then you can use this property, and Shivesh will exactly answer to your question, that you can actually get nice kernels using this. How is it useful? I mean, as I told you yesterday, there is this metric dimension problem. This immediately has implications for the metric dimension. It tells you that, you know, if you take any set, and now you want to give a different profile to everybody in your graph. Well, I mean, there will not be that many profiles, right? So you need a large set in some sense. That's what it tells you. And yeah. So it is useful. It tells you, well, I mean, you know, quite a large one. Gives you a lower bound for this metric dimension. All these locating dominating parameters, which I mentioned yesterday also. So these are dominating sets where everybody in your graph should have a different neighborhood in the domain set. This also shows that they must be quite large here. By the way, this implies for them a constant factor approximation immediately. Just if we take all the vertices of your graph, it's a trivial one. But since the optimum size is at least linear, then you will get a constant factor approximation for bounded expansion graphs, which is not the case in general. There are, like set over, there are within log n in general graphs. So it does have a lot of implications, and I mean this is actually quite recent. I mean this is quite. I mean, okay, the theorem is from 2017, but it's still an active field of research. So in the tutorial, I gave you a lot of these open questions. For example, for planar graphs, we still don't know the optimal, profile complexity of planar graphs, and also neighborhood complexity. Neighborhood complexity, by the way, is always a bit more tricky. Maybe you have realized by using problem 1 in the tutorial. It's a bit more difficult to get these arguments. In fact, all these proofs, they usually work for profile complexity, the upper bounds. They give orthogonal on the profile complexity, which immediately implies neighborhood complexity. But to pin down the neighborhood complexity is a bit more tricky. So some problems are still open in the area because of this fact. Any more questions? If not,
This is the mean of it, what is that? L P1 plus P2 is less than 2D. This is the
length of P1 plus P2. This is the path I obtained by concatenating P1 and P2. So this was just witnessing that if you take the blue and the purple path, since the blue has length D and the purple has length at most D also, you take them in a sequence, it gives you a path. It might not really be a path, there might be some repetitions, but it doesn't matter. You can take a shortcut if you can, but the length is at most 2D. That's it. Which is a witness that this guy is in the weak reachability set of this guy, with 2D as a parameter.
So that
That's
means
exactly.
that this is the mean of next line after this.
S is the minimum of it, of the path.
Or leftmost you mean.
This is
Of
P2.
P2.
Yeah. Yeah, of P, which is concatenation. Of P1. So this is what this was my goal. Okay, so now I will ask Shilesh to give us one nice application of this neighborhood complexity to kernelization algorithms on graphs of bounded expansion. So I think it's nice. I mean, I haven't worked on the topic. He has been working on that, so it's really nice to have an expert here so he can tell us firsthand what's going on, what kind of problems people are trying to solve, and are able to solve in that area. Is the screen visible? There's a button to switch on.
Alright, so let me tell you, even if you missed something or you did not follow any proof, I will not assume that you know anything in this talk. So this is a self-contained talk in some sense, and I also try to abstract out a lot of details. So if you go and see in the paper, then there are a few more things. But here I sort of just gave you the essence of the kernel so that you know what is going on and how to use the technique which Flora mentioned recently. So this is a joint work with my PhD supervisor Bart. I was a PhD student at TU Eindhoven, and currently I am a postdoc at IMSC with Sake. Some of you were asking about the picture. Okay, I will explain you why this picture, but okay, just to give you a bit of a detail, is like this is the sunflower growing on the surface of the moon. This is what generated by Mid-Journey when I asked this question when I was supposed to present this during a conference. To get the context, maybe ask me later during the lunch. Okay, so let's start with science. Let's recall what kernelization is. So kernelization for any parameterized graph problem, think of it any your favorite problem. Suppose vertex cover. You have a graph G and you want to find whether there is a vertex cover of size k. So what it is, it's like a algorithm, first of all, and the algorithm takes polynomial time. And what it outputs you, that you give any graph G with where you are looking for a solution of size k, you shrink it to a smaller graph in poly time, where the number of, where the size of this reduced graph G prime is now bounded by some function of k. Okay? And what property we want between these two instances? We say that, okay, gk is a yes instance if and only if g prime k prime is a yes instance. What it means for gk to be a yes instance? Okay, with example of vertex cover, if you have a vertex cover of size k here, then you also have a vertex cover of size k prime there. That's what it means. So it preserves the answer for the problem. And yeah, as I mentioned, the g prime is bounded by some function of k, and k prime is not large than what k is not. And this function, the bond that you get here is generally called the size of the kernel. So whenever I will use linear vertex kernel, then it means that this is the order of k. Okay? So one more thing, if at any point there is something unclear, just feel free to ask questions in between. So I have few things, but okay, if you still want to ask some questions, I don't want to go to till end and finish it. I will better give you some idea till say half of the lecture, even if time runs out. But if it is clear, that is more than sufficient.
So does everybody know what's a parameterized problem?
Given that in this lecture we have seen lots of them, I assume that some of you know. But if someone has a question, then a parameterized problem, as I mentioned for a vertex cover, you have like a parameter with the input instance. You have a parameter associated with it, which is any say positive number. Here we are looking at, for example, for vertex cover, we are looking at solution size as a parameter. It could be anything, any positive number. Okay?
The treewidth, for example.
Yeah, treewidth, for example, that we have seen. So k dash is always smaller than k, that we demanded here. So if you give a bond on f of k, then it also implies a bond on f of k dash. So generally, we give a bond on, because, okay, in this lecture, for example, we will see the k dash and k remains the same. But just for the sake of completeness of the definition, I mentioned this detail because there are problems where you reduce this parameter. Okay. Is this definition clear? Okay. Now let's look at a problem called triangle packing. So what you have a graph G and you have a positive integer k. For example, assume k equals to 2. And now what you want to do is you want to find k vertex disjoint triangles in this graph, in the input graph. For this graph, it's not hard to see that for k equals to 2, it is a yes instance. These two triangles are basically green are the triangles. But for example, if you ask for 3, even though there are 3 triangles, they are not vertex disjoint. So it is a no for k equals to 3. Okay? Note that this this problem generalizes maximum matching. Because K2 is exactly the maximum matching problem. Okay? But this problem is not like maximum matching. You can compute maximum matching in polytime, but this problem is NPR. Okay? Now we will show that this problem admits cubic kernel. Function of k that I was mentioning is k cube. Using something called sunflower now. I will mention all this. Okay? So this slide is the most boring in some sense because it is like I always try to put pictures so that you can visualize, but we will see pictures. But that's why I put the example. So you have a set family at H. What it is a sets over the universe U. So you have a fixed universe, and then it is a collection of sets. So for example, you have this universe numbers from 1 to 6, and then the collection would be say 1 to 3, 1 to 4, 1 to 5, and 1 to 6. And the property that you want from these sets that is like all of them are subset of the universe. Okay? Now, this thing sort of, if you go, it tries to, if you put it as a set notation in the Venn diagram, then it tries to look at, it starts to look at something like sunflower. So, note that all of them have 1, 2 as a common vertices. So, it forms something called core of the sunflower, and then other things are like non-disjoint. So, note that all of them have 3, 4, 5, and 6. So, and this is the thing which is called petal, the yellow part. Then, intuitively or less formally, the sunflower lemma gives you a bond. What bonds it gives you? That if you have a sufficiently large family H, such that the overlap between the things are not arbitrary. So you have some structure about how things are overlapping. Here the structure means like this, see, 1, 2, 1, 2, 1, 2, 1, 2 are common. But then other things are disjoint. So this is what I mean when I say there is some limited overlap. Then what it implies is that you will get such a structure called sunflower. You will get a subfamily of H which forms a sunflower. I will formally define this, but I think it's always good to see things informally so that you get an intuition before I define the formal definition. Yes, that's what we demand. And also we demand that these sets, things except the core, are disjoint. And not only we demand, this was demanded by others.
Can we have disjoint sunflowers also?
Yes, so the core can be empty. So for example, if you have 1, 2, 3, 4, 5, 6, okay, I don't have more things in the universe, but yeah, suppose if you have up to 10, then 7, 8, 9, they themselves form a sunflower with empty core. But it could not be like, okay, two things are intersecting, say there is one here and there is no one here. So there should be some structure in terms of how the sets are looking. Like a bramble. Not quite here. So bramble is something more different. Like there you don't expect that. There the overlap can be arbitrary. So two set can have 1 and 2 set can have 2 in the bramble.
This is a bramble with cover 1, but every bramble is not a sunflower.
This is a bramble with cover 2, no?
I think every
One because
cover 1.
Oh, cover 1. Yeah, okay. The definition was it's heating. Yeah. So this implies a bramble. Okay, I wouldn't still say. Because bramble has this specific definition that it should be touching and all. Here you don't demand any touching thing. So this is a set system, and think of it like hitting set kind of thing. So this, by the way, has lots of application for the hitting set problem and all. Okay, I will now formally define what a sunflower is. Sunflower with k petals, S1 to Sk, with the core X, is a collection of sets, as I mentioned informally, such that each of them, if you look any Si and Sj, their intersection is exactly X. So nothing outside the core. And the set S minus X, this yellow part is called petals of the sunflower. was shown by Adolph and Rado that if you have a sufficiently large family, now the numbers come into the picture. That what we mean. So first of all, if you have a family with size d sets, okay, for our previous problem we had three things, okay, and the H is sufficiently large, means d factorial k minus 1 to the power d, then it contains sunflower with k petals, okay, and more importantly, it can be computed in time polynomial in size of the family and the universe and k. Why it is more importantly? Because we will use it for the correlation, and correlation, recall that we said that is a polynomial time algorithm. Okay, so we say classical result, and it has lots of application in correlation as well as parameterized algorithm. Is this clear? Okay. Then let's see how can we use the sunflower lemma to obtain something that I claim, that it has a cubic kernel, the triangle packing problem. Okay. So we start with this family to be the set which contains all the triangles in the graph, which you can compute. Now, as long as the set size is 3 factorial 3k plus 1 to the power 3, just to work out this number, this sunflower lemma guarantees you that there is a sunflower. Okay, and it can be computed with 3k plus 2 petals. Call them S1, S2 up to S3k plus 2. Okay? Now, I will say that, okay, this S3k plus 2 petal that we obtained is not important in some sense. So what it is telling you is like we can still forget that triangle. There are lots of triangles forming as a sunflower, and then we can forget one of the triangles from the graph, from the triangle pattern. Note that all these sets, S1, S2, S3k plus 2 are triangles because each of them belong to this H. And H was the set containing all triangles of G. Okay? Now,
X is counted just by taking all three tuples and for whether it is triangle or not.
yeah, one way of doing it is like just see all three tuples of the graph, check whether that forms a triangle. If it forms a triangle, you can just put it in the edge.
So can we assume that core is empty because we want the packing problem, any two triangles don't share a vertex. So are we assuming that when we apply the sunflower lemma here, so are we assuming that X is an empty set?
It need not be. Note that we are not removing core. What we are removing, so there is a important distinction here. That's a good question actually. So note that we are not removing the vertices from the graph. We are just removing this triangle from the set H. So if there is another triangle which contains the core, we still keep this core. Because eventually the reduced graph is graph induced on the reduced H. So you enter into this while loop. As long as you find a sunflower, you try to remove a triangle. And removing a triangle does not really remove the corresponding vertex from the graph. Because vertex will later be defined. So when you get the sunflower with 3k plus 1 petal, you already know there are, in fact, not one, 3k plus 1 representative of this guy, which ensures that the core is there. Because if you remove this, then it will not work actually. So if you remove the core, it will not work. And we also don't know if, because there is at least I don't know of a sunflower lemma version where you explicitly ask that core has to be empty. It could be like the core has say one vertex of the triangle. Let's say two edges outside and vertices here.
The set is a vertex set only or like take graphs, subgraphs only?
Which one?
Let H be the set containing all triangles of G.
So you can think of it like all triplets which forms a triangle, which was like asked by Saraswati that how to enumerate. You can just look at all triplets of the graph and then check. Okay, this is clear?
Why do we remove this S3k plus 2?
We will see the correctness now. So we will see that it is safe. What I mean by safe? Recall the definition of kernelization. We said that we can reduce it to a smaller graph while ensuring that if you have a solution of size k, means if you can pack k triangles in the original graph, you can also pack k triangles in this reduced graph. But now you have probably less elements. If you start with any arbitrary graph, you have a bond on one triangles. Because this bond is exactly the k cube in some sense, asymptotically. Some fixed number here and there, order k cube. Okay? Alright. So we will see exactly the question that you asked. Why we remove this and why is it safe? Okay? We will show that if you have a triangle, then there is also a triangle, like k triangles, disjoint triangles in the reduced graph. For that, assume that we had a solution in the graph which contained this triangle. Because, okay, there is one more thing going on. It's like I assume that you just apply it once. Not that when you are in while loop, you can apply multiple times and you can forget lots of things before you enter, before you exit. But assume, I will give you the correctness for the one triangle, like one petal removal of the sunflower, and then that implies basically the correctness for the, like, so you can assume that you have an intermediate graph G1. So Gk is yes. Once you remove the one triangle, that is yes, and then so on, you can apply. So let's assume that we just remove one thing in this while loop. Okay? And the one thing that we removed was actually part of a triangle. That is only the problem, no? If that one thing was not part of a triangle packing, then you already have other triangles. So that itself is a solution. So if it was a part of triangle, then note that any triangle you have in the graph, by definition, we know that any triangle hits at most 3 of the petals. Because petal is disjoint and triangles are disjoint. Is this argument clear? So, any triangle will hit at most 3 petals. Okay? And how many triangles we have except this guy? And note that we already, since we have a solution, we already ensured that the core is part of a solution. So now, no triangle can intersect core. Because these triangles are in some sense disjoint. So, okay, I abstract this out. This is also sort of a triangle, for example. Because the triangles in the solution are disjoint, so nothing is intersecting now core. And everything that intersects things in this sunflower is intersecting with at most 3 things, which is important. But how many things we had? 3k plus 1. We had a solution of size k. So in fact, okay, so it can hit at most 3k things in the sunflower. So there is one thing which is free. Let's call 3k plus 1 thing is free. All the other things you hit. I mean, this is just a guarantee. You can also do with smaller numbers. I mean, 3k minus 1 plus 1, but let's not go that much into detail. And I try to simplify it. That's why I said that, okay, let's just do with 3k plus 1. Okay, so there is one thing which is free. And this is a triangle pattern. So all we care about is like, is there free things which we can replace? So you have some k minus 1 thing lying on the graph somewhere, say here, somewhere else in graph. Now, okay, this guy I removed, but I will find a replacement with this guy now. So what you can do is like, okay, you remove this S3k plus 2 from the solution that you got. You just add this S3k plus 1, which we know is then context disjoint, given the argument that any thing intersects with at most 3k petals. So this gives you cubic kernel. Now you can see this is a cubic kernel. This proves that it is a yes distance. One direction I showed, other direction is easy. In the subgraph, if you have a k disjoint triangles, then the larger graph you already have, so that is not very interesting. But interesting thing about this one is like it can also be adapted for the weighted setting. It's not hard to come up with this. You have to just ensure that here you do not arbitrarily delete S3k plus 2, but delete that as triangle which has the minimum weight, so that this replacement argument works. I will formally define what a weighted problem is and all. But yeah, the crucial observation is like this replacement should work so that you can find a solution which was at least not as, which is at least as good as what you have earlier. Yeah. So Faraday sunflower, now we will say that S3k plus 2 is the triangle with the minimum weight. You remove it, you can still find the replacement. Because what we replace this with is not bad than what we had. Disjointness we already argued, and then the whole thing should work. Okay, so this is the nice thing about this kernel. So this implies that weighted triangle packing also has a cubic kernel on general graph. Okay? Is this clear? Sure.
So we are saying that there is some 3k plus 1 which is empty, which is not intersecting with any of the triangles. And we know that there are k triangles because it is k distance. Okay. So, but we don't know where they are because, so how do you know that this is the one which is empty and you are replacing it with this? There will be one which is empty. But how do you know it?
That's a good question. Okay. So, if you look at it, first time, I mean, expect that this question should arrive, and note that this sunflower itself is not the whole graph, right? So there are, say, triangles here. But what you know about these triangles, they are disjoint. That is the crucial thing. Then you get the structure. That since these triangles are disjoint, you cannot hit first of all the core. We already assumed that this core
One
along
of them can hit the core.
suppose if someone hit the core, then you have two triangles. In the solution, what did we ask? These are the like the solution are the collection of disjoint. Because I show you the example with 2 and 3. Even though the graph had 3 triangles in the beginning, it is not a yes answer for the problem. Here, like when I define the problem. Note that there are 3 disjoint triangles, but this does not have a solution because they have to be vertex disjoint. Right?
Yes, but one of the disjoint triangles can hit the core and others cannot hit the core.
Yes, that's exactly possible, but that's what that's the thing that we are taking, right? We assume that this set is contained in the solution. That's what we started with. If this set is not contained in the solution, you already, like, the removal of this set does not change anything. So you already assume that this is a solution. So it implies this is the one which hits the core exactly. Of course, one can hit. But now you know this one already hit the core, so no other thing can hit the core now. Is this clear?
So this is the triangle in the solution, right? In our solution, this green triangle is in the solution, right?
Yeah, this triangle is the solution.
So a solution triangle can also hit 3 of the petals.
Of course. That's why I put this 3 papers. So this vertex can be said here.
Yeah, it is at most 3, right?
At most 3, but you know this is a triangle packing it. At most 3 things to hit.
So that's why this is 3 equals to 1.
Yeah, that's why. So you know that any k-side solution will hit at most 3 k things. So there is still 1 3 things. Okay? Okay? Sure.
So there is one free thing I agree. How do you find the free thing?
So that's why we assume that whenever we say that it is a yes instance, if and only if it is a yes instance, we don't give you the argument of how to find this. All I'm saying is like if you know how to find a k-side solution in the ordinal graph, you also know how to find a k-side solution in this reduced graph. So that is guaranteeing, like that is what we are guaranteeing by.
In the reduced graph, you are using the solution, right? We cannot.
So this is existential proof.
But we are not using the. So in the existential proof, the reduction should not depend on what the solution is, right?
Of course.
It should depend that solution exists. So I know
Yeah.
that something exists, some petal exists which is not intersecting with any of the triangles. So if I don't know which petal exists, how do I say that remove this petal and now add escape this back?
I said that you can arbitrarily remove any factor.
Any petal?
Yes. For the unweighted
Yeah,
set,
that
it
is
does not
the-
matter.
Okay.
And even arbitrarily removing any petal is sufficient to ensure the answer.
Okay.
So, and why it is sufficient? So, do you remember this very simple kernel for the vertex cover? With it says that, oh, if you have a vertex of degree k plus 1, since if you do not pick that vertex into the solution, all of the neighbors has to go to solution. So you immediately said that, okay, just pick this into the solution and then remaining should go. But now when I'm saying, I notice that this is not a good example of the thing that I want to mention.
So I think the argument is that take any hypothetical solution.
Yes.
Okay, you don't know how it is, but
Yes.
it is there.
But
And then you can always kind of modify it so that it doesn't use that vector. This is basically what. There's always a vector that you can ensure that some solution, maybe that solution uses the vector, but you can find another solution which would not use the vector. I think that's the argument. No?
If it's still unclear, let's discuss this probably during lunch. Because this is the crucial fact of correlation algorithm. I mean, this uses the existential thing. All you are ensuring is like if you have a solution of size k in the original graph, you have a solution of size k. We do not guarantee how to find it. So correlation does not, because for NP complete problems you can't guarantee that I will find it in the reduced graph.
yes, definitely.
Right? So in some sense it is just existential proof saying that if you had a yes instance of the problem, then you still have a yes instance of the problem. It's up to you how you come up with the thing. I am just guaranteeing that this is a yes instance of the problem. So if you know how to find in the original graph, you also know how to find in the reduced graph. But now the reduced graph is quite small.
But reduced graph should not depend on the solution of the original.
Reduced graphs should not depend. In terms of k, it depends. If you had a solution of size k,
In terms of which thing is empty, it should not depend on.
No, it doesn't.
Maybe I'm understanding the reduction wrongly. So is it happening in the reduction that we are removing S3 k plus 2? Now we are finding something which is empty. Now removing that and adding this again. Is this the reduction?
no.
You
Reduction
just
is-
arbitrarily deleting something.
Just discard something. That's the
We are
reduction.
not removing S3 k plus 2.
We are removing from the set.
We are
Yes.
removing any arbitrary S3 plus k S3 k
How
plus
can we remove arbitrarily?
That's what I give you a proof of, no? You can remove an arbitrary S3 plus 2. That's the proof. Why can you remove? Because you can find a replacement. Okay, let's discuss this offline. I will mention you the details. Probably, I think there is some confusion about finding a solution and ensuring that solution space is yes and if and only if it is yes. So we will discuss this probably during lunch. Okay. So what we saw is like there is a polynomial time algorithm which given an instance gk of triangle packing outputs an equivalent instance g prime k such that the number of vertices in the reduced instance is bounded by order k cube. So this is a cubic kernel for the problem. But okay, so this is what I claimed and this is what we achieved. So let's go back to where we were. So we know this thing, but it is like now a natural question to ask like, okay, well, for this graph we know cubic kernel. People try, but about okay, which other graph class has say linear kernel for the triangle packing problem? Then for planar and graph of bounded genus, Bodlander et al. Using a seminal result of meta-kernelization so that it admits a linear kernel. Okay. Then for bounded expansion graph class, there is a recent result by Ahn et al. They show that not only this problem but even a more general problem admits a linear vertex kernel. Okay. Now what we studied is something called weighted triangle packing. Note that sunflower lemma works for the weighted setting, but here there are some complications. Let me first define the problem, then we will see. So now what you have? You again have G and K. You wanted to pack K triangles. But apart from that, you also have node weights on each of the vertices. So for example, 1, 3, 2, 1, all these are weights on the nodes. And now you have a threshold T. So you want to find K vertex disjoint triangles with total weight at least T. For example, if you have this graph and K equals to 2 and T equals to 7, then the same thing is a answer. Which is a yes instance. You can sum it up 3, 2, 5, 1, 6 and then 3, 3, 9. So it's like it satisfies. Whereas if T is sufficiently large, so that you don't have to sum and check, then it is a known state. So in some sense, this problem is hard. Even though you had a, see, for k equals to 2, you had a solid yes answer in the unweighted setting. Now the subspace is more. Now you also have to ensure that the total weight has to satisfy this threshold requirement. Okay? It generalizes triangle packing. You said just weight 1 and T equals to 3k, it's sort of the triangle packing. It has again k-cube vertex kernel using the sunflower lemma argument that you don't arbitrarily remove a petal but just remove least like the minimum weight one, because that will ensure that if you have at least 3 things, then you have at least 3. And now we ask the main question. On which graph the weighted triangle packing admits a linear vertex? Okay? Now all the techniques that we saw in the previous slide by Bodlander and Ahn, this sort of does not work very well with the weighted setting. Okay? What we saw along with Bart is like weighted triangle packing admits a linear vertex kernel. So it is basically matching the best that you can get in unweighted setting.
One question about weights. Can we give weights to the edges and then the problem is equivalent to this problem, or is it a completely different problem?
Okay, let me think. This is a good question. But if you have a triangle, k disjoint triangles in the original graph, can you ensure that there are k disjoint triangles in the line graph? That I don't know. Edge weights, I am not quite sure. So probably the sunflower lemma argument will still work, but with the setting that we are using, we have to ensure few things to see if the edge weights work. But vertex weight setting works. Sunflower lemma argument probably works because you just replace with things which are okay.
And what about total weight less than equal to T? So you are studying about greater than equal to T. Total weight greater than equal to T.
Yeah.
What about if it is weight is less than equal to T?
Pack any triangle, it will satisfy
No.
yeah, G triangle will satisfy, but I think what he meant is like also you need to satisfy k, like pack at least k triangles. So probably it will fall into the min-max thing, but okay. I don't know immediately. So you want to ensure that you still pack k triangles, but ensure that the weight should not go to the...
Yes, like minimization.
Maximum. If you make the all the weights
Negate-
negative,
Yeah, I was thinking about that, but
negate all the weights.
yeah, negate all the weights and try to find the things. Probably, I mean, that kind of argument should work. I think.
I mean, sunflower lemma works.
Yeah, sunflower lemma works. So let's look at, so not only we saw that there is a linear vertex kernel on Bondage-Wilson graph, but there is also almost linear vertex kernel on no-verdence graph. Okay? Let's see how we will come. Fine. So yeah, we will focus on how to get order k vertex kernel. And our result is not just like, okay, let me tell something before passing to the next slide, which is more fun. So our result is not only gives you something for a general graph, but it also is much simpler algorithm than those complicated notion for the unweighted setting itself. So this is like in some sense it is generalized problem in the unweighted setting, weighted setting, but still it is simpler than what you can achieve for say planar or bonded genus graph even in the unweighted setting. Okay? So let's define something. So given a set P of a graph and a vertex outside P, we say that, and just fix a number R. We say that a vertex is in R projection of V if there exists a path such that the internal vertices path does not belong to P, and there exists a path from V to that vertex of length at most R. So for example, if you look this V and if you set R equals to 2, then these red things are in true projection from this vertex V to P. Note that this is not. Even though there are length path of length 2, internal vertex belongs to the set P. So I will denote this using M subscript R for the radius where we are looking at, and the vertex and which set we are looking at. Okay? Now what we know about the boundary expansion graph class is like this set is not large, as in you start with the set P of boundary expansion graph class, then you can compute or you can efficiently enrich this set. Maybe this set itself does not have some property that we wanted to find, but you can enrich this set into say P star, which is a superset of P, such that you have the property that if you look from this vertex, the thing which are at a distance R for any fixed R is sort of bounded by a fixed constant. Let's call this alpha. And this was a result by Rangatel, who sold the first kernel for this bounded expansion and lower dense graph classes. Okay? Is there any question?
So does this follow from this neighborhood complexity, or is it a different argument?
This uses basically the similar kind of argument like neighborhood complexity, but I'm not quite sure that how the proof goes.
So alpha is a function of R, right?
Yes, it is function of R, but we already assumed R is fixed. So this is a constant in that sense. Of course, alpha is a function of R, but it is, for a fixed R, it is fixed number. So that's why it is sort of, we will see. That's why it is like in lots of applications where you look at a distance R dominated set. For a fixed R, you can compute this kind of set, and then this set is helpful. Let's see why it is, how it is helpful. And another property that you have is like the number of distinct R projections. So that this one thing is called the one projection. So there could be lots of R projections in terms of the subset. A priori on general W to 2 to power P. But here the number of distinct R projections on this set P is bounded. Once you enrich this set, then it is bounded. And that's why you need some enriching argument.
If we have P, why you need P star?
Why you need?
P star.
Because to begin with, you probably don't have this property. Right. So you want to enrich this set so that because this R projection is in some sense a bit different than because this R can be general R. So it's not just neighborhood, it is distance R neighborhood. Okay? Using this, let's see how to get a linear vertex kernel for unweighted triangle packing. And the same argument that we gave for the sunflower lemma, because we will use sunflower lemma. So let's look at the unweighted triangle packing. Although I told you that we have a result for weighted triangle packing, but okay, just to simplify it, I will present it for the unweighted setting, but it's not hard to see it will also work for the weighted setting. What we do first is like, first of all, we compute a maximal greedy packing of vertex joint triangles. Just pick a triangle in the graph, remove it from the graph, again look at it. Okay? If this packing is self-large, you are already a system. Okay? So now assume that this packing is small, but then you have this nice property, and this is used mostly in all the packing kind of problems in kernelization. That now this set is bounded by 3K. Okay? And what you know other than that is like this graph outside of this set is triangle free. Because there is a greedy maximum packing. Otherwise you would have added that triangle into the set.
Less than or equal to 3K, right?
Sorry?
It's not a strict. It should be less than or equal to.
No, I already said that if you have at least 3K, you are already done.
You have a budget of K, right? And so
be even lesser, but I don't want to complicate this slide by giving another 3 to a k minus 1 and 3 into k minus 1 and things like that. As long as it is like 3k, we are done. Like it will work. Now we will increase the set that we mentioned, like in the previous slide. We will increase the set. Let me go to this so that we have the things here. So we will increase the set P that we have obtained. This was the packed set. Now we increase the set so that these two properties satisfy. What the first property is? The size of P is not much large, which means the P was bounded by 3k, so P star is also bounded by 3 order k. Okay? Because P star is order of P. And now the nice thing is, like, if you look at the distance to neighbor from V, in the sense that internal vertex does not contain things from P star, then it is bounded by a constant alpha. This is from exactly the thing that I mentioned in the previous slide.
How is order of BP linear in K?
So what was the size of BP?
Yeah.
3k, right? So it is, and what it is guaranteeing you, you start with a set P, then it is it gives you something which is a constant times size of P. So you already have 3 times k, and again you have one more constant. So 3c k. Okay? Now you have this. Now what we will do is, like, now we partition based on this. Because note that this set is in some sense small. If we have to ensure that the overall graph has only order k vertex, then we have to ensure that everything outside has order k vertex only. This set is small. What we are aiming that in overall the whole graph there should be order k vertex. So we already have, in P star we already have order k vertices. Outside, if we ensure that there is order k vertex, we are done. So what we do first is, like, we divide this into equivalence classes based on what they see in P as a distance to projection. Okay? Now ensure that, like, note that if we partition into this equivalence class, the number of things are again bounded by order k. This is the property of class that we mentioned in the previous slide. So the number of distinct arc projection is bounded by order of k, which Florian was also mentioning during the lecture. And where are we going? Just to give you the sense of direction, we note that we have k. We have still, these things are also order k. Many boxes here, which are equivalence class. If we somehow ensure that each of the equivalence class has a constant many vertices, then overall we have order of k things. Now, so to achieve that, we will apply sunflower. Okay? What I mentioned just now is exactly in this picture. You know that these things are order k. Maybe this set is very large. But okay, now all I want to ensure is, like, there is a constant many things which we need to keep, and then remaining things we can forget from the graph. And still ensure that if there was a k disjoint triangles in the graph, then there is also k disjoint triangles in the graph, excluding these guys. Then the numbers will work. So our goal is to somehow ensure this thing. Now we'll apply sunflower lemma. We again collect all the things with the triangles. Now this is a special thing. We want to bond the number of triangles that we have intersecting with this set. So we call HI as the set of triangles that intersect with the vertex of CI. Okay? Because we wanted to bond it to be the order k, we will try to now apply the sunflower lemma with 3 alpha plus 2 sets. Why this 3 alpha plus 2? You know, the number of things that you are seeing here is alpha, bonded by alpha for any equivalence class. Because alpha is the maximum of what they can see. And since this graph is triangle free, you can't have any triangle here. So every triangle has to intersect here. Right? So there can't be a triangle here, every triangle is intersecting here. So how many disjoint triangles you can have with an equivalence class? At most alpha, right? Because here is the alpha many things. So that's where the intuition of sunflower lemma comes. So if you have at most, recall, if you have at most k, then we ensure that 3k petals is sufficient. So you can discard one of that. Here now, see, this is a constant. So just 3 into that constant number plus something, just for the Pearson's principle to work, is sufficient. Because you know that with one class now the intersection is small. Is this argument clear, or it's like not that? Okay, I assume that is here. Then we discard this 3 alpha plus 2. Again, we are in arbitrary setting, we discard any thing which is as good as. But for the weighted setting, again you discard this. Now, same way, that's why I gave you the kernel, cubic kernel for the general graph. The same way we find this set, this thing. Now, now we don't find 3k plus 2, but now we find 3 alpha plus 2. And now we will prove the correctness. Based on what I mentioned. All I was giving you was an intuition key why it is correct. Now, like let's see formally why this thing is correct. 3 alpha plus 2. Okay? So what we want to prove, if you have a solution of size k, means if you have k disjoint triangles in the graph G, then you have a k disjoint triangles in G prime. Where G prime is the graph where you remove, say, these things. Okay? So now again assume that you have a thing which contains this removed vertex from the sunflower lemma. Now since one triangle, similar kind of one triangle can hit at most 3 things, and you know that number of triangles with one equivalence class, because note that we ensure that all of these are from the same equivalence class. One triangle, this is triangle free, one triangle from this equivalence can have intersect with at least one vertex here. So we can have at most alpha many triangles, these one triangles from one equivalence class. So we know that there is 3 alpha plus one thing, so there is at least one thing which is free. So one thing is free means like, say 3 alpha plus one thing, one is free, then you can find a replacement argument. This will simply work for the weighted setting with the change here. Alright. So that's about what we achieved. Note that this is not quite complicated. Especially if you have to go and read the result of, say, what the other people have found, then you will notice that this is much simpler than, say, using protrusion replacement and those kind of things for even for planar graphs. Okay? So, there was this first result in this area by Drange et al. For R dominating set. Now the question is like, oh, can you find a set such that either a vertex is in the set itself or at a distance R from the set. So this is like standard dominating, you just want neighbor, now if you want at most R distance from it. So they show that it admits a linear kernel on bounded expansion graphs. Then they also show that dominating set admits a almost linear kernel. Almost linear means you give me any epsilon, I will give you k to the power 1 plus epsilon kernel. But they were not able to say for R dominating set. But the nice thing they show that okay, this is the graph class where the things stop. So in that sense it is interesting. If you go beyond the low dense graph class, then it ceases to exist. Like this kernel is ceased to exist because this is W2 hard. Which even if you don't know what W2 hard is, it means that you cannot expect to get a kernel. Leave out polynomial or linear. So this is exactly the graph class where this tractability between where you get a linear kernel or where there is no kernel at all. Then later on, since it was just for dominating set, later on it was shown for R dominating set by Ekmer et al. In IGA on low dense graph class. Then, yeah, this is the slide to let you know what are the literature and how it progressed over the time. Then for R independent set, Klipchuk and Siebert show that it admits almost linear kernel on low dense graph class. Again, the R independent set is like set of vertices such that if you look any two of them, there is no path of length at least greater than equal path. Okay, and all the other result uses so this all of them was generalized in the sense that they studied a more general problem of PRF packing or PRF fitting. Let's not go into details, but okay, all these things are generalized by Arnikel, which is in ISO 23. But all of them uses something called uniform quasi-wideness property, which is another way of characterizing the sparse graph class. But it is very complicated. I mean, at least in terms of correlation, if you go through that, it is much more complicated than what I mentioned. So if you feel lost, probably you would have much more lost if there is a kernel projected using uniform quasi-wideness. What we did is like we find for the weighted setting, but now it does not rely on uniform quasi-wideness. It just uses sunflower lemma and a simple notion of neighborhood complexity. So what we saw is like weighted click packing on bonded expansion graph class admits a linear vertex kernel.
Can you go to the previous slide?
Sure.
So this last level is so you generalize from the triangle to the arbitrary clips.
Yes, and I sort of, that's why I said when I said that I abstract a few things just to make the thing life simple for the purposes of this talk, but you can generalize it for clip, any clip. Triangle is a K3, but I mean
But fixed leak or any size?
for a fixed T. So you already know what thing you are packing. So for example, if you're packing KR for a fixed R, then you can get a
Conflicts of same size. Splits of same size.
yes. What we believe is like we can also do it for general graph edge. I have to write down the details still, but okay, this could be done. Just for extra information. So it need not be a click. Okay, so what we saw is like click packing, weighted click packing on bonded expansion graph class admits a linear vertex kernel. You just have to modify that statement of the sunflower. Then it can also be extended to get almost linear kernel. I didn't go into that because it is just a bit of like, we also don't know much about the no weighted graph class for now, and it is like a bit more calculation in terms of 1 plus epsilon which is coming on the factor. Now the open question is like, can we get for the covering problem? So now you want to hit all triangles. Now you don't want to pack because these things are dual. Instead of covering, can you like packing? Can you do it for covering? But for weighted setting, there is this complication where the weight arrives. If you are interested, you can ask me later on. I will discuss what is the complication. But for now, if you have any question, just feel free to ask.
The unlimited case is easy.
Which one? Covering. Covering. Yes. The Arnikel paper that I mentioned, which generalizes all the previous results. That sort of this result. Yeah, this one also is for covering. Not only just for packing, it also works for covering. So for unweighted, this is known.
What is the base known for general graph for weighted case packing?
General graph.
It's better than
You don't know KQ better than KQ. Sunflower lemma gives you KQ, but in terms of number of vertices, it's a wide open problem whether you can improve it for a general graph. That's what I think. If I did not miss any decent work, then it used to be wide open and probably still is a wide open problem. Can you even get 3, yeah, K to the 3 minus epsilon for a general graph? And why this is nice is that you get linear here in these graph classes. Leave over QD. Alright? Any more questions? Okay, thank you.
Could you please share this? Sure. And may I go to the website here?
Yes, sure.
Okay. Okay, thanks Suresh for the nice talk on how to use this neighborhood complexity. I mean, as you have seen, this definition of neighborhood complexity was not exactly the same, but it's the same ideas anyway. It was using these projections, which is not exactly the same as the profiles. But, so, as usual, I had planned too many things, so I was thinking it would be a bit shorter, and I will have planned for time for another proof, but I guess not today. So the thing I was planning, maybe I'll skip it entirely. It was also an algorithmic, not just algorithmic, but how is the relation between these distance d dominating sets and distance d independent sets in graphs of bounded expansion. And we can actually use these weak coloring numbers again to show that between these independent sets at distance d and domination sets at distance d and graph classes of bounded expansion, there is some kind of nice bound. So of course d independence is kind of a lower bound for the dominating set, but some dominating set will be some constant away from the independent set as well. So this is quite nice. Not true in general, but true for bounded expansion classes. But actually in the tutorial number 9, there's a nice and simple argument which gives you, okay, it doesn't relate with independent set, but at least it will give you an approximation for the dominating set. And I think this is, I mean, I had initially put 3 stars in that thing, but now that you have seen all these proof techniques, it's again, use the minimum and this path and so. Another application of this technique, so it's not that difficult, I believe. Anyway, you can try, we can discuss it. Yeah, so there will be one final lecture tomorrow. I have to still think what I will tell you in 2 hours, but okay, my idea is kind of also to wrap up and maybe give you some sense of directions, what else exists there, because it's quite rich. Maybe we can finally make sense of this picture. I think we have all the arguments now to see these graph inclusions. So maybe I'll spend some time with this and maybe show you a couple of definitions, but only just so that you have a sense of what else exists in this field. It's quite rich. And of course, I mean, you always have these lectures by the Philip Chuk brothers, which we have given links to, which is even has much more content. So if you're interested, you can watch them. Of course, for this week, I was quite inspired by the lectures. Okay, so this afternoon we have one tutorial, which is, I mean, there's no more problems. The tutorials are complete. At least the questions are complete. Solutions, hopefully by tonight. Will be there. So in the afternoon we'll just continue. We can, I think for the sheets of this week, there is enough material to think about the bounded expansion, the coloring numbers, these neighborhood complexity. There's a lot of questions. So we will continue with that. And then tomorrow there'll be a final tutorial, but basically, I mean, it works today also. I'll just come with all the questions and we'll try to answer. And tomorrow afternoon, I think my plan will be I'll be here in the department. So any questions you have, you can stay there and ask maximum number of questions before this week is over. So please ask questions, even the very simple ones. I mean, even if you didn't get the very basic definitions, it's always, you know, even I will feel nicer if you, at least I see that you have understood after that you ask me the question and then you understand, hopefully. Yeah, and we are hoping that maybe tomorrow we'll organize some lunch, closing lunch. So maybe we are thinking of ordering some pizza or something.